Hi everyone. In this video, I'm going to be giving a demonstration of some of the basics for performing multiple linear regression using RStudio. So I'm not going to be going into all aspects of multiple linear regression or its interpretation, but some of the basics in terms of running the analyses. So if you check underneath the video description, you'll find a link to an SPSS data file that I'm going to be using in this video. Basically, we will import that SPSS data file into RStudio and then work from that. So that data file will be saved when it's imported as a data frame. So the first thing that we're going to do is go ahead and set our working directory in RStudio. If you go up to Session and go to Set Working Directory, you can click on Choose Directory and locate a folder on your computer or on your drive where you want to save any work and so forth. Usually, it's a good idea just to set the working directory in relation to whatever data set that you will be working with. So I'm going to click on Choose Directory here, and this is the folder that RStudio is pointed to right now, and the data is actually in this folder. It's MLM reg in my documents folder on my PC. So you can't see the data set yet. We're just busy setting the working directory. So when you click on open right here, you'll see that it appears down at the bottom. It says set working directory. That's a function. And you can see the path leading to that folder. And I'd actually already set it previously. So now what we will do is import our data. So I'm going to go to File, Import Data Set, and go down to From SPSS. So we'll click on that, and this import wizard comes up. I'll click on Browse, and you can see this is the data set that we're going to be working with. So multiple regression EX2. So I'm going to click on Open right there. And you can get a data preview, and you'll see there's a little code preview down at the bottom. This is actually calling up the Haven package that is used to import data into from SPSS into R. And then you can see next there's a read SAV function, or read underscore SAV function with essentially referring to that data set that we were talking about. And because R is already pointed at the folder that contains the data set, we don't have to include the path to that right here. So you don't actually have to do anything in terms of code or anything. I'm just kind of explaining what this is. And so what will happen next is that once the data is read in, it will be saved to a data frame called multiple underscore regression underscore EX2. And so we could change that name if we wanted to over here, but we'll just leave it as is. So we'll click import. And so now the data has been imported. You can see in the environment tab in the upper right corner of the screen, you'll see it says multiple regression. It's got 50 observations on 6 variables. So that's just, that's what you see on the left in the upper pane. So now what we will do is we're going to open the script editor. So I'm going to go to File, New File, and then our script. So when we click on this, we get a script editor. And this is where we will type our code in and run our analyses and so forth. So it's more efficient than if theoretically we could type our code in down at the bottom in the console below, but you can really only type one thing at a time. It's not as efficient. So I tend to prefer the script editor above in the left upper pane. So at this point, what I'm going to do is I'm going to go ahead and use a library function and call up a couple of packages. So if you haven't already installed them, you'll want to do this. But I'm going to type in library, and one package is lm.beta. And then the next one will be, we'll type in library, and then jtools. And so these are just some supportive packages, supporting packages that I thought I would show you as I'm going through this presentation. So these aren't going to be for the main analyses, but just there are a couple of things that I wanted to show with that. So again, be sure that if you to have installed these packages, if you haven't already done so, you would do this by typing install period packages, excuse me, and inside parentheses you would type in the name of a package. So we would type in lm period beta right there, and then we would do the same thing for the other package, jtools right there, and they both need to be in quotation marks. So to install them, I already have them installed, but I'll just quickly run this, and it goes through the process of installing them. So in a second, it will finish up. So you can see down below. All right, so now both are installed. So now we need to load the packages. So to use packages in R, you have to load them. So that's using the library function. So we will highlight both of these and click on run. And so now you'll see that they are basically ready to go. So at this point, we will transition into running a multiple regression. First, though, let's take a quick look at the structure of our data. We can already visualize the data right here under this tab, but let's use the structure function. We'll type in str and then the name of our data frame. And the name of our data frame we can kind of go back here. You can see what it was. It's this multiple underscore regression underscore ex2. So we can type this in right here. And once you've done this, then highlight it and click on run. And just kind of taking a look at it, you can see it's saved as a tibble, which is a type of data frame. You can see that the variables in here we have a variable for female, gender identification, basically a variable coded 0 for male, 1 for female. We have a variable that is referring to motivation intervention group. So that is actually going to be treated as a factor variable in our regression analysis. You'll also see that we have variables, subject matter interest, there's mastery goals down there, and anxiety, and student achievement. And so basically all of these variables right now have been read in as numeric. You can see the characteristics of these variables as numeric. And it even turns out that the the gender identification variable was read in as numeric, as well as that motivation intervention group. And so that would be a problem if we run our analysis without accounting for the fact that this should be treated as a factor variable. So at any rate, we could also, if we wanted to, we could take a look at the first few rows of data using the head function. If we type in head and then the name of our data frame, which again is multiple underscore regression underscore ex2 right there. If you highlight this and click on run, you can see so it's giving our output kind of using that the tibble kind of formulation. So you can see that you got female gender identification. Basically, we just have the zeros and ones. This is for the first 6 rows of data. For motivation group, we've got group 1 right here. There's a group 2. There's a group 3 that's represented for case number 6. And the labels associated with these are showing up as well. Then we've got our subject matter interest variable, mastery goal variable, anxiety, and achievement. So in our analysis, we are going to be predicting student achievement as a function of some of these variables. And so the first analysis that I'm going to run is just going to include continuous predictors. So we're going to basically predict student achievement as a function of subject matter interest and anxiety. So another thing to kind of note too when you're using RStudio or you can use it would be the same. You can type in comments. So and in the script editor, it's really handy to include comments as you're going along. This can be used for documentation purposes. So to use a comment, just type in a £, and then you can follow it up with various comments. So you'll see it shows up in green. So I'm going to type in linear regression with continuous predictors. Okay, so now, so if I try to run this line right here, then basically it just shows up in the output below just as a comment. So you're not going to get an error message or anything like that. If you don't include the £, and it shows up in black right there, if I highlight this, click run, I'm going to get an error message. So be sure that you include that £. Okay, so now let's run our analysis. So I'm going to type in, I'm going to create an object. I'm going to call it OLS1. And we have our assignment operator, and basically that is a lesson sign followed immediately by a hyphen. Okay, so on the right side of this, we're going to use the LM function, or linear model function, and inside the parenthesis, essentially there are going to be two main arguments. The first argument is going to be referencing a formula, and the second argument is going to be referencing the location of our data, or the name of our data frame. So our formula is going to be specified as follows. We're going to type in achieve, which is the name of our outcome variable or dependent variable and which is in our data frame. Then follow that up with a tilde. And so then to the right of this, you are going to type in the names of your independent or predictor variables. So I'll type in SMINT and plus and anxiety. So make sure when you're typing in your variable names that you know, any letters that are supposed to be in caps are in caps, and anything that's in lowercase is in lowercase. If you incorrectly type in, if I typed in with a small a right here instead of a large a, and I try to run my analysis, it's not going to work. So R is very picky about you know, whether your variables are using upper or lower case. You need to make sure that they correspond to how they're laid out in your data frame. So after we've specified our formula, again, basically achievement is being regressed onto subject matter interest and anxiety. We'll type a comma, and then we'll use a data argument. So we'll set this equal to the name of our data frame, which is multiple underscore regression underscore EX2. So we'll put this in right here. And so when we run the analysis, by the way, the function LM is going to be applied, and then any results that we generate are going to be saved to an object called OLS1. Okay, if we don't do this, by the way, and I'll just show you what happens, we end up with some output, but just a subset of it. So just to show you what I'm talking about, if I highlight this and click on run, I end up with the coefficients like the intercept, the slope for subject matter interest, and the slope for anxiety, but nothing else. So to get a more full set of output, I want to save all of this to an object. So this object, I'm going to call it a fit object, if you will, but it's just basically an object. I'm going to call it OLS1. And so that's just an arbitrary name that I'm using. There's nothing special about it. I could have called it any number of things. So now what I'll do is use the summary function, and inside parenthesis, I'll type OLS1. So if I highlight this and click on run, you can see that first off, I need to actually run the whole batch because I had not run that previous line. So I need to run the whole batch. And so now you can see that I get my output. So you get, you know, just basically what I typed in up here. You can see that I've got the unstandardized regression coefficients that are given in the estimates column. I have the standard errors, the t values, and then you can see the p values that are given over here. With those p values, you can also see that there are asterisks that are given, and then kind of a little indicator of significance down here based on those asterisks. So as you're looking at this, you can see that also, by the way, you've got the multiple R square. So basically the set of these two predictors account for about, if we multiply this by 100%, about 37.48% of the variation in achievement. You can see that the F statistic is equal to 14.09. The degrees of freedom due to the regression is 2. That's equal to the number of predictors. The degree of freedom or degrees of freedom residual is 47, and you can see that we have a p-value right here. So if you're reporting on the F statistic, you can see that we have statistical significance where the set of predictors are accounting for significant variation in student achievement. When we look at the individual predictors, basically subject matter interest, we have a positive unstandardized regression slope. You can see that our t-test results, we have statistical significance. Anxiety, we have a negative slope, and we have also a significant slope as well. So in effect, basically students scoring higher on subject matter interest were predicted to score higher on achievement. Students who are scoring higher on anxiety were predicted to score lower on achievement. So both of those were statistically significant. Keep in mind too that the intercept in the model is the expected or predicted value on y when your predictors are all equal to 0. So oftentimes this value is kind of treated as a nuisance parameter, particularly in those cases when values of 0 are not observable in your raw data on your predictor variables. But if you were to do something like mean center your predictor variables to where they are centered at 0, or centered so that the mean of those variables are now 0, then in that particular case, the intercept would be interpretable. So at any rate, something else I want to show you then is a function associated with the lm beta package right here. So just keep in mind that to use this function, you've got to call it up, and that's why you had to use the library function up here. So just really quickly, we'll type in lm beta, and inside parentheses, I'll type in OLS 1. Okay, so when I do that and highlight it and run, then I get standardized regression coefficients from this model. So up here, we had just generated the unstandardized regression slopes by using the lm beta function. We get the standardized regression slopes. And another function that you might find useful is to utilize a function that's associated with the jtools package right here. And that function is sum. So it's spelled S-U-M-M. So if you type in S-U-M-M and then OLS1 and highlight that, click on run, then you get your output. It looks a little bit nicer than what we had before. You could even use a digits argument. So if I type comma digits, set that equal to, let's say 4, and highlight it and run, you can see that now we get our estimates that are rounded off to 4 decimal places. You can see that we have our model fit information. There's the F test results, the R-square value, and adjusted R-square that's given right here. If it's the case that you want to add in the fully standardized regression coefficients in your output, then you can utilize a couple of arguments. We'll add in scale and set that equal to true. You can either type in the full word true in all caps or just T, that will work. And then a second argument will be transform response, set that equal to true as well. So if we highlight those and click on run, you can see that we get our results. And looking in the estimates column right here, the regression slopes are exactly the same. So this also the t-values and p-values that we had seen up above are repeated down below. Keep in mind too that if you utilize this approach, the intercept is going to be 0 in that case, just like it was above when we generated the standardized results. You can see that the intercept is given as NA down below. So another argument that you might consider including is particularly in those cases if you're concerned about heteroscedasticity or non-constant variance of the residuals, is a robust argument. If you type in comma and then robust and set that equal to, there are several different robust estimators. We'll use inside the quotation marks, we'll type in HC3, and the H and the C are in caps. So if we highlight, click on Run Now, you can see that we get our robust estimators, the robust standard errors that are printed out. And actually, I'm going to get rid of this part right here and just request this in relation to our unstandardized output, just so that it makes a little bit more sense to us right there. So again, we have our output, we have robust standard errors, HC3 standard errors. So these are the unstandardized regression coefficients divided by the robust standard errors, gets us the t-values that you see right here, and then there are the p-values. So that is another option that you can use. Again, you would use that in those cases where you have concern, or you want at least to prevent problems with heteroscedasticity affecting your standard errors and thus possibly affecting your inferences regarding the regression coefficients. So at any rate, I've kind of gone back and just typed in a comment right here indicating that these are, this is the function associated with the jtools package. And then right up here, I've added a comment that lm.beta is associated with the lm.beta package. So and I will make sure that underneath the video description, I'll include a link to a document that will contain this code that I'm going through. So that's the reason why I'm including those comments right there. So the next thing that I want to do is I want to run my linear regression, and I want to add in motivation intervention group. So let's say that our students had been exposed to one of 3 motivational interventions, and the idea is to see if maybe that had an impact on their achievement. And we'll also control for subject matter interest and anxiety. So in this particular case, now if I use the well, I'll go ahead and type in OLS. I'm going to call this 2A right here and enter an arrow. Then I'll type in LM and then achieve tilde, and then I'll type in mote int gp, that's the variable name, plus smint plus anxiety, comma, data equals, and then multiple underscore regression ex2. So there it is. Now, if I do this, this is going to be a problem, because right now, when we read our data in, it's being recognized as numeric. So this variable should be treated as a factor variable and not numeric. So I'm going to add a little comment right here just to say OLS regression where mote int GP right there is incorrectly treated as numeric. So I want to show you what it looks like in terms of the results, and then juxtapose it against a correct specification of it as a factor. So we'll go ahead and we'll also add another line. We'll type in summary, use the summary function, and I'll type in OLS to A. So we'll highlight these. I'll even include the message there, and you can see our results. So you can see that there's only one regression slope for the motivation intervention group, and that's because what's happening is that when we imported our data, it was being recognized within the data frame as being numeric, or being treated as numeric instead of a factor variable. So keep in mind that it doesn't make any sense to treat this variable as a continuous variable. And so what we want to do is to actually recode this variable into a set of dummy variables that carry the grouping information. So in terms of this variable, we had three levels. We had intervention A, which was coded 1, intervention B, which was coded 2, and intervention C, which was coded 3. So as we're thinking about this, just kind of keep in mind that we have our treatment variable right here, and we had the value codes of 1, 2, and 3. And I apologize, I don't have my little notepad writer with me right now. But so we have our treatment variable. That's the original motivation intervention group variable. So that's our treatment variable. And so one thing we can do is we can recode this variable into a set of dummy variables that are included in the regression analysis. So the first dummy variable we could recode, we'll just say the first and the second dummy variables will carry all the information needed in order to identify the different treatment groups. So the first dummy variable we might code 0, and then 1, and then a 0. The second dummy variable we could code 0, 0, and 1. And so by virtue of this coding of the two dummy variables, you can see that treatment group 1 is coded 0 on both of the dummy variables. Treatment group 2 is coded 1 on the first dummy variable, 0 on the second. Treatment group 3 is coded 0 on the first and 2 on the second. So if we add or include these dummy variables in our regression analysis, what you'll end up with are regression coefficients that can convey the difference in student achievement, controlling for the other predictor variables between groups 1 and 2, which would be reflected by the regression slope for this dummy variable, and between groups 1 and 3, reflected by the regression coefficient for this variable. And just kind of keeping in mind the coding, a positive slope for D1 would indicate that treatment group 2, or basically intervention B, would have a higher mean than treatment A, or intervention A. If we happen to have a negative regression slope, that would indicate that the conditional mean for intervention B is actually less than that for A. And so the same general logic would apply for that second dummy variable as well. So what I'm going to do now is kind of go back over to our script editor, and I'm going to add another comment here, and I'll just say mote int gp correctly treated as a factor variable. So there are a couple of ways that we can do this. Oh yeah, by the way, I'll add in another comment. Group 1, or intervention A, is the reference category. So I'm going to be kind of following along with that dummy coding scheme that I just talked about. So if I type in OLS, I'll type in OLS2B. I'm going to create a new object called OLS2B. Type in LM, achieve tilde. Then I will go ahead and type in my covariance, subject matter interest, plus anxiety, then plus, and I'm going to add another argument, or excuse me, I'm going to add the factor function. So I'm going to type in factor, and inside parenthesis, I'll type in the name of my grouping variable, which is MOTINTGP, motivation intervention group. So what's going to happen is by virtue of including this factor argument right here, which we're going to apply that to the motivation intervention group variable. And by default, it will utilize the dummy coding system that you see that I just went through. So essentially the variable the value that's coded 1, the lowest value, is going to be recoded as the reference category or baseline category. The second value will be coded, 0, 1, basically 1 on dummy 1 and 0 on dummy 2, and then the third category will be coded 0 on dummy 1 and 1 on dummy 2. So now we will type in a comma, and then we'll again use our data argument, and then just type in the name. So we'll type in multiple regression underscore ex2 right there. So then we'll type in summary. We're going to use our summary function, type in OLS2B right here, and highlight, click on run. And so now we get our results. So as we're looking at this, pay attention to the fact that, we still have our R-square value that's given. Basically the multiple R-square is 0.4642. Basically, as a set of predictors, they are accounting for about 46.4% of the variation in student achievement. The F statistic is 9.745. Our degrees of freedom are now 4 and 45 for degrees of freedom regression and residual respectively. P-value would be considered less than 0.001. This is in scientific notation, by the way. As we look at the individual predictor variables, you can see that subject matter interest, again, is a positive and significant predictor. And you can see anxiety is a negative and significant predictor. Now, when we look next, you can see that we have factor. It says it's referring to our variable name, and it's got 2. Okay, so this is group 2. Then you've got factor, and it's referring to group 3. So this isn't referring to the estimates that you see right here are not in reference to just that group, but it's actually a difference. You'll notice that group 1 does not show up anywhere in here. But actually what's going on is that by virtue of the dummy coding with group 1, it's coded 0 across both of the dummy variables. So if you keep in mind that the intercept is equal to the predicted value on y when all of your variables are equal to 0, then you could essentially interpret this value right here as the predicted achievement score for a student who received intervention A, or basically in group 1, who scored, had a value of 0 on subject matter interest and anxiety. Again, by itself, there can be some problems with interpreting the intercept if a value of 0 doesn't really make sense in terms of the original scaling of those variables, and it's not something that you can observe in your data. But, had we mean-centered those predictor variables, then we would have been able to interpret the intercept, whatever that value would have been, as the expected value or predicted value on in terms of student achievement for a student who was in intervention A and scoring at the mean or at the means on subject matter interest and anxiety. But nevertheless, as you're looking at this regression slope, the first regression slope right here, this would be the difference in the predicted means, or the difference in the predicted values on student achievement between a student in group 2 or intervention B relative to intervention A. So in other words, if you think about the coding on that variable, on that particular dummy variable, a value of 1 is associated with group 2. So because this coefficient is negative, that's actually telling us that a student that was in group 2 was expected to score lower, about 1.67, 9 points lower on achievement than a student in intervention group A, or group 1. The next regression slope is a positive value, and that's basically indicating that a student who scored who fell in group 3, or intervention group C, if you will, was predicted to score about 4.02 points higher on student achievement than a student in intervention group A. Neither of these dummy variables, though, were statistically significant at the conventional 0.05 level. Now, something else that you might want to do, in this case right here, we just have a test of each of those dummy variables, but we don't actually have an omnibus test of the overall effect of motivation, intervention, group. So if we wanted to do that, we could certainly do that by utilizing another function, which is the ANOVA function. If you type in ANOVA, and inside parentheses here, you refer to we can refer to the OLS 1, that's our previous model that did not include our factor variable, and OLS 2b, which does include our factor variable, which that's the model that we just ran. That's the fit object right there. Then if we highlight this and click on run, then we get the f-test. This is essentially performing a hierarchical multiple regression. And so this f-test that you see right here, this is basically a test of the change in R square. So you can easily pull the R square values out of the output from each of the models. From the second model, the R square was 0.4642 right there. From our earlier model that just had subject matter interest and anxiety, the R square was 0.3748. So you could just basically take the difference in that. And then the test of that difference would be this F test that you see right here. Now, let's say that we wanted to change our reference category, our reference level. So one thing that we would need to do is to convert our original variable, motivation intervention, into a factor variable, and then utilize a relevel argument or a relevel function in order to change the reference category. So by default, if we use this factor function right here, we're going to get the dummy coding scheme that I was just talking about before. So what we'll do in this particular case is we are going to change our reference category. So I'm going to add a code comment right here, changing reference category. So to do this, we are going to first, so I'll just say step 1, save our variable as a factor variable. Okay, so in doing this, what we'll do is we will type in our original variable name, but we do need to reference the data frame. So keep in mind that we have to be very explicit when we're using R and RStudio because even though we may be working with a data frame and running our analyses, we have to be explicit because the program will not automatically recognize the variables that you're working with unless there is some explicit reference to the data frame. So that's why you have this reference right here. Each time we ran our analysis, we included that data argument. So in this case, it's not structured in the same way. What we'll do is we're going to type in the name of the data frame. So it's multiple regression EX2. Keep in mind those underscores. Those are going to be important as well. And then we'll type in our assignment operator, less than sign followed by the hyphen there, and then type in factor. So we're going to use the factor argument right here. And inside parentheses, again, we'll type in multiple regression EX2 with the underscore. Now, the other part of this, right now, both of those are referencing the data frame, but now we need to reference the actual variable. So to do that, in both of these, we're going to add a $sign. And then to the right of the $sign, we type in the name of our variable. So I'm going to type in mot GP. So MOTINT GP. So we'll do the same thing over here. So just keep in mind that we can't just type in the name right here and then the name right here without reference to our data frame. Otherwise, we'll end up with an error message. So that's why we have our multiple regression EX2 data frame name followed by the $sign, then followed by our name, and it's appearing on both sides of the assignment operator. Just this one right here is within the parentheses, and we're applying the factor function associated with it. So we'll highlight this and click on run, And so now that variable should be a factor variable. And if we type in str, or structure function, and then refer back to the data frame, we'll highlight that, click on run. Now you can see that there's our variable, and now it's registering as a factor variable with 3 levels. So there you go. So now at this point, we are ready for step 2. Step 2 is to use the relevel function. Okay, so in this particular case, what we will do, oh, and by the way, I'll just kind of show you something else too. If we use the table function up here, we'll just type in table, and then we'll type in all of this. We'll reference again our data frame name and the variable name right there. We'll type in, we'll put that inside the parenthesis and highlight it. You can see that we have our levels 1, 2, and 3 that are given along with their frequency counts. So now we're going to use a relevel function, and in this case we'll type in again all of this. We have to reference our data frame, $, and then the name of our variable. So all we're going to do is kind of save over our original factor variable with a new releveled factor variable. So I'm going to type in my assignment operator, and then we will use the relevel function. So relevel, inside parenthesis, we'll type all of that in as we had done before. Then we'll type comma, and then we'll go to the next line. We'll type in ref, and we'll set this equal to 3. That is the value code associated with the third group, or the third category, or basically intervention C. So if we highlight this, click on run, then let's go ahead and just add the table function. We'll type in table, and then again our data frame name, $, and variable name right here. In this case, if I highlight it, click on run, you can see that now category 3 appears first, followed by 1, and then 2. And you can see again those frequencies are the same as before. So we've reordered the categories, and we're treating category 3 now as the reference category or baseline category. So let's run our regression. We'll type in OLS 3, then basically everything that we had kind of previously, we'll type in lm inside parenthesis achieve tilde SMINT plus anxiety plus, and now in this case we don't actually have to use the factor argument. We can just type in mote int gp right there, and then we'll type the data argument. Data is equal to, and then we'll type in multiple regression, multiple underscore regression underscore ex2 as before. And we'll also use the summary function, then OLS 3 right there. We'll highlight all of this, click on run, and so now you can see our results. So as we're looking at the results, you'll want to pay attention to the fact that, basically the R-square value and the F-test, all that's exactly the same as before in our previous model, OLS 2B. All that's the same. The only difference, or the only differences that we will see in this case, are going to be the intercept values as well as the regression slopes. And in this case, we have our dummy variables, but things are a little bit different here. To kind of show you what I'm talking about, let me just kind of go back. I'm going to kind of clean this off just a bit here. And we're going to say that our reference category is group 3. So that category is assigned zeros on both of the dummy variables. Then group 1, which you can see the first dummy variable, we have group 1 right there. That one is coded 1 on dummy 1, 0 on dummy 2. And then the second dummy variable is referencing we have group 2 kind of in the name right there. That is coded 0 on the first dummy variable and 1 on the second dummy variable. So in this case, basically the intercept that you see right here is going to be the expected group mean for group 3, or the expected mean on achievement for students that received intervention C, or basically the third intervention, and who also scored 0 on subject matter interest and anxiety. And then the regression slopes right here are differences between, say, group 1 and group 3, and then group 2 and group 3. So in both of these cases right here, you know, the different basically students that were in group 1 were predicted to score about 4 points lower on achievement than those in group 3. And then those in group 2 were expected to score about 5.7 points lower on achievement than those in group 3. You'll notice too that the second dummy variable is not statistically significant. However, the first dummy variable in this model was not significant at the conventional 0.05 level, but the second one was. So there is a contrast there that was statistically significant. Okay, so that is going to wrap up this video presentation. Again, the data set is underneath the is going to be linked underneath the video description, as well as a document that contains the code that I've just covered. I'll also include the R file as well that's associated with the script editor. So again, that wraps up things, and I appreciate you watching.